Welcome to Standard Normal Calculations. This is part of our statistics unit where we've been talking about normal distributions and normal curves. So you need to know what a normal curve is and the percentages involved before you watch this video. So we have this person, Richie, who's studying probabilities associated with rolling 4 six-sided dice. Richie rolled the dice 1,296 times and recorded their sums, so he's adding up all 4 numbers on the dice. Richie's results are shown in the table and histogram that follow. So first of all, look at the histogram, right? Does that look familiar? Along the x-axis, he's recording the sum of each roll. And then out of the 1,296 times that he rolled it, the number of times that sum appeared is the y-axis number. In the table, he adds one more piece of information. He calculates the probability of each sum. Okay, that should have said sum. He calculated the probability of each sum. So that's going to help us out with our next questions. If I were looking at this, what looks like a normal distribution, and I was asked to estimate the mean, where would we look? Well, in a normal distribution in a normal curve, the mean is smack dab in the middle. So I would probably estimate a mean of 14. Why do you think it's more likely to roll a sum of 10 than a sum of 5? Think about the the six-sided dice, the 4 dice, right? If you roll 4 dice and add the total, how often do you think you'd get a 5, or how many different ways could you get a 5? And how many different ways can you get a 10? Well, there's probably way more combinations. In fact, there are more combinations of ways to get a 10 than to get a 5. So it's more likely that you're going to get a sum of 10. And if you look in the chart, he got a sum of 10 80 times and a sum of 5 only 4 times. That's a big difference. The third question asks, what's the probability of rolling a sum greater than 20? Greater than 20 does not include 20, by the way. Keep that in mind. Remember that Richie's already calculated the probabilities of each sum for us. So if I want to find the probabilities of getting a sum greater than 20, I would take all of the probabilities for sums greater than 20 and simply add them together. When I do that, when I add those 4 probabilities together, I get a probability of 0.0270 or 0.027. We're going to write our probabilities today as decimals, but be very aware that that means 2.7%. And finally, what about if I wanted to find the probability of rolling a sum between 10 and 15 inclusive? Inclusive means that we include the probabilities for 10 and 15. So I'm looking for all the probabilities from 10 down to 15 and including the probabilities for 10 and 15. All I need to do is add those probabilities because Richie's done all the legwork for us, and I find a probability of 0.5671. So I have a 56.71% chance of rolling between a 10 and a 15. The histogram shape should look very familiar to you right now. That's a normal distribution, right? So I can use normal curve data to help me figure things out. There's lots of similarities between the distribution of the 4 six-sided dice and a normal distribution. Normal distribution is a powerful tool for analyzing data for businesses and industry. Governments use it, right? There's tons of places. Physical and social sciences use it. There are a lot of places where normal distribution is used, so we're going to continue today by learning a tool that's going to help us use properties of a standard normal distribution for any normally distributed data. So before, we had to have exactly data that was 1 standard deviation away or 2 standard deviations away from the mean. But what if I have data that's, say, negative 0.3 standard deviations away from the mean? That changes things up a bit, and the tool that we're going to use to help us with that is called a z-score. Remember, you need to know what standard deviation is before we kind of get into this. So if you haven't watched or haven't learned standard deviation, that's going to be important. You'll want to pause and go do that. So the definition of z-score that needs to go in your notebooks is the number of standard deviations that a given score is above or below the mean. So z-score measures how many standard deviations we are away from the mean. There's a formula for that. We have Z stands for z-score. X stands for the data point or number we're trying to find the z-score of. We subtract mu, which is the mean, and then we divide the whole thing by the standard deviation. In our workbook, we can find the following examples, so you can follow along if you'd like. Our first example is in the 2012 Olympics. The mean finishing time for the men's 100-meter dash finals was 10.10 seconds. The standard deviation was only 0.72 of a second. That's really fast. Usain Bolt won the gold medal with a time of 9.63 seconds. Assuming a normal distribution, what was Usain Bolt's z-score? So let's go through this. Z-score, remember we use our formula. We're trying to find the z-score for Usain Bolt's time of 9.63 seconds. So this represents X. We subtract our standard deviation, 10.10. Then we're going to divide the whole thing by our standard deviation of 0.72. I just said that totally wrong, right? We subtract our mean and then just divide by our standard deviation. So getting that job done requires me to remember the formula, plug in my values. You always want to do to solve what's on top or in the numerator of your fraction before division. So I'm going to do 9.63 minus 1010, hit equal before I divide by 0.72. And I get negative 0.65. That tells me that Usain's z-score, or his time, was 0.65 standard deviations below the mean. He was much faster than the average person. So now that you know how to kind of find z-score, you can use z-score to calculate probabilities for normal distributions when our values are not perfect standard deviations away from the mean. So for instance, let's say that I want to find the percent of values or the percent of data in a normal distribution that's more than 1.2 standard deviations above the mean. As we get further into this problem, I want you to keep in mind that when it says more than, we're also talking about any outliers that are to the right of that score. We're going to use the z-score table in your workbook to help us find your solution. So we're going to turn to page 7 in your workbook and take a look. Remember, the standard deviation I'm looking for is 1.2, and I'm going to call that 1.20. You'll see why in just a second. So in a z-score table, down the left-hand side of the chart, this measures my z-score, or the beginning of my standard deviation. Across the top gives us the hundredths place for our standard deviation. So if I'm looking for a score of 1.20, first I go down the side of my chart and find the 1.2. Then I go across the top and find the 00 that represents the hundredths place for my z-score. That's going to lead me to this probability right here, 0.8849. 0.8849 is the percent. Now take a look up here. It's the percent of data that is to the left of that standard deviation. So keep in mind that your z-score table always gives you information to the left. The probability here is 0.8849, or 88.49% of my data. Is that what it asked for? Not really. There's a negative table too. We'll get to that in just a minute. So remember, the area to the left was 0.8849, or 88.49%. That's not the portion that it asked us to find, right? It asked us to find everything to the right, including any outliers. Well, out of all of our data, we have 100% that represents every piece of data I could ever want. So when I need to find the data to the right of a standard deviation, I need to take what's in my z-score table and subtract it from 100. The percent of data that's to the right of 1.2 standard deviations is 11.51%. This is the answer I'm looking for. So let's look at an example. Let's say that we have a population of human body temperatures, right? That means we've measured hundreds, maybe thousands, maybe tens of thousands of body temperatures, and we found that they were normally distributed with a mean of 98.2 and a standard deviation of 0.7. What we're asked to find is the percent of temperatures between 98 degrees and 99 degrees Fahrenheit. So first of all, let's find out how many standard deviations away from the mean we are when we're at 98 and 99 degrees. Z-scores are going to tell us how many standard deviations we are away. So for the 98 degree temperature, finding my z-score, I get negative 0.29. For my 99 degree temperature, finding my z-score, I get 1.14. So I'm looking for on my normal curve, the percent of data, 1, 2, 3, 1, 2, 3, that's between negative 0.29, which would be about there. This is my mean here in the middle. And 1.14 standard deviation. So I'm looking for the percent in here. Here's kind of my shaded area, right? I'm looking for the area in gray. So for the 1.14 standard deviation, I find on my z-score table a probability of 0.8729. For my negative 0.29 z-score, or standard deviations, I look in my z-score table and find a probability of 0.3859. Well, how do these relate? How do I get the area in between? I'm going to subtract, right? If you look at this big score right here, or the big gray area, I'm going to take away this much of it, right? Because this is the area I want. Well, this probability over here for the negative 0.29 is exactly the probability I need to remove. So I'm going to subtract the two probabilities to find the probability in between. So when I do that, the 0.8729 minus the 0.3859 leaves me with 0.4870. That's the probability of the shaded area I was asked to find. 48.7% of my data is in that gray shaded area. We're going to skip this part. We're doing this part in class. For example 5, we're going to learn how to do mean and standard deviation using a graphing calculator. We're going to do that part in class, so if you've missed class, make sure to come see me and I'll show you how to do that. All right, come to me with any questions that you have. I hope you have a fantastic day, and I'll see you next time.